Hey, hi. In this particular video, we'll be talking about Catalan number. So Catalan number is nothing but this series 1, 1, 2, 5, 14, 42 and so on, which is governed by this closed form formula C of n equal to 2n choose n divided by n plus 1. Okay, so there is this closed form formula that finds out any nth term of the Catalan number series. Okay, Catalan number also follows this recurrence relation that C of n plus 1 is equal to summation over I equal to 0 to n C of I, C of n minus I for all n greater than equal to 0. Okay, and C of 0 trivial is defined to be 1. Now, why are we studying about Catalan number? So in a lot of problems, the recurrence boils down to this form of formula where we have summation over its own f of I and f of n minus I. So in those scenario, what turns up is the result can be directly found out to be Catalan number. Okay, and it's important in competitions to recognize this kind of functions and quickly come up to that. Okay, we can find out a order n or order 1 formula for the nth number of this sequence. Okay, so we'd be analyzing some of these cases. The first one where this Catalan number originated from is this path where you cannot go over the diagonal. So let's discuss the condition that we have put on this walk. So we are given this walk from 0, 0 to n, n such that we can never go above the diagonal. So a path which is in green, which is the border marked by green, marks the boundary, like you cannot go over this point or you cannot go over this point, so on. Okay, now the path in blue is one which is valid because it's always below this green line. You can touch the green line but you cannot go over that. So this is a valid path. A yellow one would be an invalid path, right? So since over from this particular point you are going above it, so it's an invalid path. So the number of such paths that exists in an n cross n grid is called Catalan number. Now, what is this number? Let's quickly look at what if any path that crosses this diagonal and then reaches to n, n. What if we flip the diagonal on this axis in this fashion? So when it crosses some I, I, it goes to I plus 1, I plus 1, right? So what if we flip the whole path after this across this particular axis? So this yellow path over here becomes this red path, right? So any particular path that crossed this diagonal and when was flipped across this, instead of reaching this n, n point, it reached this n minus 1, n plus 1 point, right? So the total number of paths that exist in this n cross n grid that reaches this n, n point from 0, 0 is exactly 2n choose n, right? And the number of paths that cross the diagonal has a 1-to-1 correspondence with the number of paths that exist that reach this n minus 1, n plus 1 point, right? And that can be found out by 2n, n minus 1. Now why is this 2n choose n minus 1? So since there is n minus 1 number of right moves and n plus 1 number of up moves to be made, so out of the 2n moves that are there, how many moves are we taking right, or where are we basically taking the right? Which of the moves of 2n moves are the right moves? That governs the number of ways to reach n minus 1, n plus 1, and that's how we are getting this particular formula. And if we take this particular expression over here, if we resolve it, this comes out to be 1 by n plus 1 2n choose n. Okay, so this is the combinatorial meaning of this Catalan number. So number of paths that are consistently below this diagonal is, if someone asks you to count the number of such paths, that is nothing but the Catalan number. Okay, so now you can like readily give up the answer without even like doing some sort of DP solution for this type of problem. Okay, so now once we know this particular standard example, we now need to understand what are the different scenarios where the problem resolves into finding Catalan number. Okay, so one famous example for this would be 2n length balanced parenthesis. Okay, so let's suppose you have a 2n length parenthesis sequence. How many of them are balanced? Okay, that's what we need to find out. So we can make a 1-to-1 correspondence between the number of balanced parentheses of length 2n and the Catalan number in this fashion. So let's say whenever we put an open bracket, we basically move right, and whenever we put a closed bracket, we move up. Okay, so in total there has to be n number of open brackets and n number of closed brackets, right? And now the condition that balance parentheses follow is at any point of time the number of closing bracket should not become more than the number of opening brackets, right? That's the only condition that it should follow. So that corresponds to this condition over here that we had, that it should not cross this diagonal, because anything over this diagonal basically means, like any point over this, that means that you had 2 opening brackets and you had 3 closing brackets, right? So that is not a valid point or valid parenthesis correspondence, right? So the number of balanced parentheses will corresponds to the number of walks in this grid. So every time you make a opening bracket, you basically move right, and every time you put a closing bracket, you move up. So the number of walks in this grid to this n comma n point from this 0 comma 0 point is actually equal to the number of balanced parentheses. So there is a one-to-one correspondence over here. So that means the solution for this particular problem is also C of n. Okay. Now let's look at few more examples. So the number of binary trees with n nodes, well, this does not correspond to that walk. How do we correspond this to the walk? So for this type of problems, you need to understand the recurrence relation that we follow in Catalan number. So Catalan number follows this particular relation that you have C of n plus 1 equal to summation of C of I and C of n minus I, right? The convolution of this. Now, let's look at what is being counted over here. So let's suppose there is a binary tree with n nodes. So you take a node over here and then you need to distribute the rest of the nodes to 2 of its half, right? So let's suppose you put I number of nodes over here and there are n total nodes. So there would be n minus 1 minus I number of nodes in this particular half, right? There is one node over here, there is I, and there is n minus 1 minus I number of nodes in this right half. So now this should be a binary tree as well. So let's suppose f of n gives you the number of this particular metric is like f of n, okay? So now if we try to find out the recurrence for f of n, so f of n is nothing but summation of, you take one of the nodes to be this root, and based on how many nodes you decide to go on left and right, this is nothing but f of I multiplied by f of n minus 1 minus I, okay? And if you look at this properly, if you just put n equal to n plus 1, this becomes nothing but f of n plus 1 equal to summation of f of I f of n minus I, right? I equal to 0 to n, right? This is I equal to 0 to n minus 1. Make sense? So now this converts to this particular summation, and this is nothing but the recurrence for Catalan number. In fact, for f of 0, this is nothing but 1, because if you have just one node, then there is just one tree, single node, right? So this follows both the conditions that are there in Catalan number, and hence the solution for this particular problem will also be C of n, like for any n node that is C of n, right? Now let's look at few more examples. So number of full binary trees with n plus 1 leaves. So when I say full, that means that, okay, there is the height of this, let's say, is h. So let's say the height is up to h plus 1, then this last level elements needs to be filled, okay? So you need to fill the last level elements. The leaves can be somewhere in this part, but everything above this particular level, let's say this is 1 and this height is h, all these nodes are completely filled, like there is a perfect tree going on up till this level, and then at the last level there might not be a perfect tree because there are some extra leaves getting added, but this is what we call a full binary tree. Now we need to put in n plus 1 leaves into this. So now when we need to put n plus 1 leaves into this, this also resolves into finding f of n plus 1. Let's say this is nothing but this f of n plus 1, and as you can see that you can put 1 into this particular half and the rest into this, 2 into this particular subtree and rest into this, and so on. So this also resolves into that same recurrence relation that we had, right? F of I into f of n plus 1, n minus I, because at least one of them has to have 1. That's how we are defining this. So the height needs to be balanced, right? So that's why we have defined this n plus 1 leaf, so that one of them will have at least both the sides will have at least one nodes in this particular part. So when you have n plus 1 over here, this is going to get into this particular relation where I equal to 0 to n, right? So, and of course, like when there is like binary trees with n plus 1 leaves where n is equal to 0, means that there are only one leaves, and that's just one unique tree, right? So that is nothing but like f of 0 is also equal to 1. So this is also the same definition of Catalan number, so hence the result for this will also be C of n, right? Okay, let's look at this particular example, that the number of triangulation ways for a convex polygon of n plus 2 sides. Okay, so let's quickly have a look at, let's say, okay, so this is a convex polygon and we want to find out the number of triangulation for this particular polygon. So let's say there is n plus 2 sides over here right now. So let's say we choose this particular side from over here, and then we have multiple choices for this base. Okay, so let's say this is the base of the triangle. So one of the triangles must have this particular side as the base, right? So let's say that triangle chose this particular side of the polygon as the triangulation point, and then this basically takes this triangle into account and it divides the two of its halves into two separate problems, that how many solutions are there for this and how many solutions are there for this. So let's take one more example. Let's say this is taken into this base, and this is the triangle, and there would be like 1 2 3 4 sides in this, and 1 2 3 4 5 1 2 3 4, right, 4 sides over this side as well. So there were n plus 2 sides, and one of the sides got removed. So based on that, we will also form two subhalves, and the number of ways of this subhalf and this subhalf would be multiplied. So we will also get, we are going to get the same type of relation again, that okay, f of, there are, let's suppose, n plus 1 number of sides, so one of them gets reduced and there is the choice of the rest of the sides divided into two of the equal halves, right? So f of n plus 1 will become, let's say there are n plus 1 sides, so if f of n plus 1 will become one side and the triangle got removed, so now there is this other faces over here, so that would be summation of f of I multiplied by f of n minus I. Okay, this is the same recurrence relation again, and if we put, like, by definition we were thinking about this particular example, so this is going to be like Catalan number of n. Okay, this is going to be the recurrence, but this is going to be the Catalan number but we define for n. So if you find out the solution for C of, for 2n plus 2 sides, it is going to come out to be Catalan number of n. There might be one or two shifts by this particular relation, so that's why we have this Catalan number of n for n plus 2, and when you put even for n equal to, let's say, 0, then there is like no way, so that's exactly like just 1, like there is the empty polygon has one way to triangulate it, right? So that's why this particular example is also Catalan number. Same goes with this particular example, that let's say there are 2n points on a circle and you want to connect them, so that you want to pairwise connect them so that no two intersect. So in this as well, you will have to take one point and match it to the one of the other ones, and then the right subhalf and left subhalf will become two separate parts, and both of them will be independent. So you will have some sort of relation where you have, like, let's say there were 2n points and then you remove 2, so let's say it became f of 2n, f of, let's suppose this side has I number of points new, and so this will become multiplied by f of 2n minus I minus 2, right? So this is how it will form, and like this particular summation will only work when I is only even, right? Because the number of points to make them pairwise aligned needs to be even, right? So this f of I is only defined for even, so everything else will be odd, so we will have only even terms in both of them cases. So if we just take out this two in, like, we define f of 2x equal to some g of x, something like this, so g of x will follow the Catalan number, and hence the solution for f of 2n will also be Catalan number. Okay, so these are all different scenarios where you see that okay, Catalan number is popping up, and in case in some problem you see that okay, this is the recurrence being formed, or this is the path that is being traced. Like there are two possible scenarios that you might identify in a problem, that there is a one-to-one correspondence between the path that does not cross a diagonal, or there is a recurrence relation where you have something like this format: f of I plus 1 is equal to summation over I equal to 0 to I. So this should be j, right? F of j multiplied by f of I minus j, right? If this kind of relation comes up in a problem, which sometimes appears, like if you look into these problems, you can think of the recurrence relation terms, and you will see that, okay, this is what is getting formed. And once you see this type of term in a recurrence relation, you need to understand, okay, this might be a Catalan number problem, and you now need to investigate into this direction, right? So this is what you should take away from this particular video, that, okay, if I see these two signals in a problem, this can be a Catalan number, right? So that's all for this particular video. Thank you, and see you in the next one.